a reminder, our triangle mid-segment theorem says that the mid-segment, so for this particular one, NP, is equal to half the length of this third side, and it's parallel to that third side. So they asked you to actually show it. So we can't just simply say the triangle mid-segment theorem tells us that. We need to actually show this to be true. So for part A, find the coordinates of the midpoints. How do we find midpoint when we're on a graph? Use the midpoint formula. Very good. So that's how I got N and P, is just simply using your midpoint formula. I drew a little sketch just to get a visual. Does not need to be accurate. You can see I didn't even put in tick marks. I just was trying to get an idea of where things were. So NP then is my mid-segment there. So if I'm looking at a graph, how do I know if two lines are parallel using a graph? The same slope. Yeah, if they have the same slope. Just back to algebra 1. So what I needed to do was show that they're parallel. So find my slope of NP, find my slope of KL, show that they are the same, meaning that they're parallel. So just in your algebra 1. Now for part C, that's the other portion of our mid-segment theorem, which says that this is equal to half the length of the third side. How do we find distances on a graph? We'd use our distance formula. So find the measure of NP using distance formula. We get 2 root 2. Find the measure of KL using distance formula. We get 4 root 2. And then we just have to show that it actually satisfies this equation. So just put it back into this equation. Oh, looky there. It does simplify down to the exact same thing. 2 root 2 and 2 root 2. They are equal. So thus we do have that statement is true.
That's crazy.
You will be seeing this again. So make sure you don't forget how to find a midpoint, how to show lines are parallel, just the same slope, and your distance formula. So you're just showing that this is true. We know it's true from the theorem, but we're showing that it's true for this particular. Okay, questions with that? That algebra 1 stuff's very important. Yes, Joseph?
So I got all of the, like, yeah, I said yes and everything. I got the points correct, but I didn't.
What did you do? You just did it. How did you show that the lines were... Did you get your midpoints okay?
Yeah.
How did you show that your lines were parallel? Good. So you showed the slopes are the same. Good. Then how did you show this part there? What'd you do? You plugged something in. What is that something? What is it? So this means the measure of the length of the distance of. So when you plugged in NP, what were you plugging in? Like, did you do the distance of it? Did you do the midpoint of it? Okay, so find the distance of it. Find the distance of it, right? Because this notation, guys, means the measure of it. We're talking about measure on a graph. That's the length of it, distance formula. Just find distance of it. Distance formula is this guy up here. Changing x divided by, or sorry, not divided by 2. Woo! Changing x squared plus changing y squared. Just make sure you maintain that order and then square root of all of that. That's the like sleepy owl thing that we talked about. It's like the minuses and plus. Other questions with Suzanne? Did you have a question? Yes, once I am not in front of it. You may now take it. Okay, so again, this is just our unit 1 stuff of midpoint and distance formula, but applied to our unit 7. Okay, do we have any remaining questions on our homework worksheet 2, worksheet 3? Awesome. Okay. I'll make sure you filter down. Yes. All right. Go and get or shoulder partner or someone nearby you. I want you to quiz each other on our vocab. So we have quite a few vocab terms, and we learned about perpendicular bisectors, angle bisectors, circumcenter, incenter, equidistant from vertices, equidistant from sides. You need to know which ones go together, which property goes with which point of concurrency. It's very important for this unit that you know your vocab, that you can identify these things, and that you know which point goes with what. So I want you to take a couple minutes, quiz your shoulder partner. The reason I put this up here so you can't see what I wrote up on the board because it's a summary of it all. I want you to quiz each other, not just what the vocab is, but orthocenter, which set of lines does that go with? In-center, which set of lines does that go with? Go, quiz each other. All right, go ahead and bring it back up front. So again, it is extremely important that you know not just the vocab terms, but that you can identify them, that you know which terms go with which, and what properties go with which. So let me pull up our vocab. Okay, so last class we talked about pretty much this first half here of perpendicular bisectors, angle bisectors, circumcenter, and incenter. So just a reminder that concurrent lines meet at one single point, and we call that point the point of concurrency. So when we draw all of our perpendicular bisectors in a triangle, they meet at one point, and we call that point the circumcenter. So that's where your perpendicular bisectors meet up. And our perpendicular bisectors, when they meet at that circumcenter, the circumcenter has a special property. What is that special property of the circumcenter? Go ahead.
It's equidistant from the vertices.
Good. It's equidistant from the vertices of the triangle. Now our angle bisector, when we draw all three of those, they meet at one single point, and we call that single point the incenter. Our incenter is equidistant from the sides. Very good. Now when we're talking about the distance from a point to the side, we talk about the perpendicular, the shortest distance. So that's why sometimes you'll see that perpendicular marking, because that's just indicating that shortest distance. Perpendicular bisectors are responsible for being perpendicular and bisecting. They're not responsible for anything else. They don't have to cut through the angle. They don't have to do anything with the angle. They just simply have to be perpendicular and go through the midpoint. Our angle bisector is only responsible for cutting the angle in half. It doesn't have to hit the midpoint on the other side. It only has to cut the angle in half. So make sure you know the distinction there. Okay, so last class, we had perpendicular bisectors meet the circumcenter, which is equidistant from the vertices. And our angle bisectors meet the incenter, and that's equidistant from the sides. Now on top of that, we also learned that our angle bisector meeting at the incenter is always going to be inside your triangle, whereas our circumcenter could be either in our triangle, on our triangle, or outside of our triangle. So this is just a summary of what we did last class. You guys in your pictures. Alright, so with the circumcenter, if it's inside, that's acute triangles. All acute triangles are inside. For obtuse triangles, it's always outside. The right triangle, it's always going to be on it, and we said specifically it's the midpoint of our hypotenuse. That's our super short shortcut we were talking about with our. So this is what we learned last class. Again, you need to know which pieces go together. Today, we're going to be talking about that bottom half of our vocab. We're going to be talking about the bottom half of our vocab.
Oh, no.
Medians and altitudes. Now, we already talked about mid-segment. That was like day 1 or day 2. So, reminder, mid-segment, this is what we talked about with our homework. Joins the midpoints. And our theorem said it's half the length of that third side and parallel to it. But today we are focused on medians and altitudes. So, who can explain to me in their own words, what is a median? Go ahead, Noah.
It's like the vertices and the midpoint of opposite.
Good. So median takes vertex to midpoint of opposite side. It doesn't have to cut the angle in half. It has no responsibility for the angle. Its only responsibility is vertex and midpoint. Awesome. What is an altitude? Go ahead, Keegan.
It goes from vertex straight down which one's perpendicular line.
Good. So it has to go vertex to side opposite in such a way that it's perpendicular. This is also called the height of the triangle, but it's vertex to side opposite, so that's perpendicular here. Okay, so that is what we're focusing on today. And guess what? If we draw all of our medians, they meet at one point. We call that point the centroid. And our altitudes, if we draw all of our altitudes, they meet at one point, and that is called the orthocenter. So today we're going to be learning similar information their characteristics, whether it's inside, on, or outside the triangle. So we're adding some more to our vernacular today. All right. So you probably need this paper called the notes before I start writing all over it.
So we're going to do send this.
Oh, and it's so sad.
No. Like, no, we're going to use these if you can't.
So that's a verse.
Um,
And that's a verse.
No.
no, not in verse style. The mid segment will come back to help us out, but we won't have it. I need to change that. All right, so coming to your day 5 notes, and this is the last chunk of our new material. Woohoo!
Is it easier than last time?
It's about the same type of stuff. Dang it!
Yeah.
I need to get I need to remove all this unit or quarter one out of black. No, because this person also maybe be organized. Like Miss Trick. She makes me organized. She's way just.
What are you saying from here, Brett?
No, I'm saying, like, when teachers make you be organized, you are organized.
Like you have to.
Like if they
I thought
grade.
I heard you say something about
Oh,
issue
Mrs.
bomb.
Drake's stuff. They thought
So I
that
heard-
Mrs. Drake's
Mrs.
stuff.
Drake.
Like,
That is what we're talking about.
yeah, climbing her nose.
Okay, is there anyone that did not get the notes? Okay. So, medians again join the midpoint, the vertex of the opposite side. That's median. Okay. Now, before we dive into the theorem, what do we call that point where all the medians meet up? Centroid. Okay. Let's go ahead and look at our altitudes. Again, an altitude connects vertex to side opposite so that it is perpendicular. And when we draw all of our altitudes, they meet at the point we call orthocenter. Does that make you think of your dentist? That's where you go to get braces, is the orthocenter. All the orthodontists are at the orthocenter. Okay, so let's take a look at our first theory. Congruency of medians. The medians of a triangle. Medians of a triangle intersect at a point. Medians of a triangle intersect at a point. What do we call that point again? Centroid.
That's crazy.
It bothers me that the theorems don't actually use the name in it, so. No, it just says the medians intersect at a point that, yeah. But I like for you guys to. Okay, the medians of the triangle intersect at a point that is 2/3. Yep. That is 2/3 of the distance. No equidistant here. That is 2/3 of the distance. The medians of a triangle intersect at a point called their center. That is 2/3 of the distance from each vertex to the midpoint of the opposite side. Midpoint of the opposite side. The medians of a triangle intersect at a point called their centroid. That is 2/3 the distance from each vertex to the midpoint of the opposite side. Let's talk about what that means. So our median, that we drew here in blue. First of all, which point represents our centroid?
C.
C.
So here's our centroid. Centroid. Okay. So basically what this does is it breaks my median up into 2/3 chunk and a 1/3 chunk. So what it says is it's 2/3 the distance from each vertex to the midpoint of the opposite side. So my centroid breaks up so that from here to the vertex is 2/3 of the whole thing. And from my centroid to the side is 1/3. So let's go real simple example here. Suppose the entire median is a length of 30. How much would the length be from D to C? 20. And then from C to J? 10. Okay. So it's not that it's the same distance to the vertices. It's not the same distance to the sides. But for each individual median, it breaks it up the same way. So the medians are not the same length. For a certain triangle, they are the same length. But in general, they're not necessarily the same length. But they are broken up the same way. They're all broken up into 2/3, 1/3 chunk. So let's go ahead and write that out in general terms. For our picture here, I would have that DC is equal to 2/3 of the whole thing, DJ. And then we could go ahead and extend from there that CJ is 1/3 of the whole thing. Oops. What was your question? That's a good question. It's always 2/3 from the vertex, 1/3 from the side. 2/3 from our vertex, 1/3 from our side. Yes.
So we can't say DC is equal to CE.
We cannot. Yeah, DC and CE are not necessarily equal. Because the medians themselves are different lengths. So although DJ I just said was 30, it's possible that EG is 50. So 2/3 that would not be the same. Okay, and then this is true for every single median in terms of the 2/3, 1/3 chunk. So let's go with our EG here. So C to E, centroid to vertex, that's our 2/3 chunk. 2/3 of the whole thing. Our whole thing is GE, general electric. Which means C to G is the 1/3 chunk.
That's money.
Then we'll do our last one here. Alright, so again, from centroid to vertex, C to F, that's 2/3 of the whole length, FH. And from centroid to side, CH, that's my 1/3 chunk. And again, when I'm saying 2/3, 1/3, I'm saying 2/3 of the whole median, or 1/3. Now, sometimes you're given the entire length. Sometimes you're only given a portion of it. So it's helpful to also recognize the relationship, not just between the chunk and the whole thing, but between these two chunks. Let's go back to our D, C, D, J, this guy here. So again, we see that DC is 2/3 of the whole thing, and CJ is 1/3 of the whole thing. But what's the relationship that I can make between DC and CJ? What can I say about this? What's the relationship?
Oh,
Vanessa?
the sum of DC and CJ equals DJ.
That is true. I agree. DC and CJ will give us the whole thing. That is good. What else can we say?
1/2 of DC is equal to CJ.
Good. So DC is 2/3 of the chunk, CJ is 1/3. So would you guys agree that 1/2 of DC equals CJ? 1/3 is just half of 2/3. How else could I write this? DC equal to what? 2CJ. Because 2/3 is twice 1/3. You don't have to memorize that. It's just another relationship that's helpful to see. That if you recognize that, in certain situations, it's faster to get you.
This is like when you said like there's only like the one type of triangle that's like where all the medians are the same distance, would that triangle be by any chance an equilateral?
It would indeed. It would indeed. The equilateral is your special.
That's crazy.
Special one.
Special one.
All right. So again, this is true for every single median. 2/3 chunk, 1/3 chunk. It's not that all my 2/3 are the same and all my 1/3 are the same, but all the medians are broken up in the same way. So let's go ahead. I'm going to skip this middle chunk for just the time being. Let's go and do a little bit of practice with numbers. So taking a look at this here, they said SP is 6 inches. So the whole thing is 6 inches. All right, the entire median is 6 inches. How much is the measure from H to S? 2. 2 inches. They said inches. We'll get back inches. And that is because this was equal to 1/3 of the whole thing. Oops, do best. Laura, did you have a question?
Yeah. It's not true for all of the triangles.
It is true for all the triangles. No, for an equilateral, you just have it on top of it that once you do all these, you end up getting the same value for each one. But it's true for an equilateral that it breaks it up into 2/3, 1/3. It's just it has an extra bonus thing that each of your 2/3 values are the same. Okay, so HS is 2 inches. How much would the measure of HP be?
4.
4 inches. Good. All right, and again, that's because that was 2/3 of the whole thing. Okay. So it's nice when the number is a multiple of 3. Divides out real nicely. But we don't live in a world only of multiples of 3, as great as that would be. So let's take a look at the next one. It says that the measure from U to R is 4 inches. So if the whole thing is 4 inches here, I want you to real quick talk with your shoulder partner. How much would HR be and HU?
HR would be 8 over 3. HU would be 4 over 3. Same thing.
You don't need this.
So HR was 1.3.
Repeating.
All right. We should have gotten some fractions, right?
Yeah.
So our whole thing is 4 inches, not a multiple of 3. Let's go with HR first. What is the length of HR? Okay.
8/3 inches.
Give me thumbs up if you agree, thumbs down if you disagree. So mainly thumbs up. 8/3 inches. You work with your units. Again, this goes back to HR is equal to 2/3 of the whole thing, UR. And so if I just do 2/3 of 4, multiply straight across, you get 8/3. Awesome. So how much is HU? 4/3.
Yes.
4/3 inches. You could do 4 minus 8/3, or just do the fact that it's 1/3 of the whole thing. And again, 1/3 times 4 gives us the 4/3. Okay. But sometimes the numbers aren't even nice like that. Let's throw in another one.
Well,
We do have to. We do.
5.
So in both of these situations, they gave us the value of the entire median. They don't always do that. So let's suppose if, let's go HT. The measure of HT is 7 inches. You know what? Why are we still doing English system? Let's go with a nice metric of centimeters.
Yes.
I wish I could just adapt the metric system, but that's okay. I heard they tried and everyone got confused and took it back. Alright, so if Harris teeter is 7 centimeters, Then how much is headquarters?
Because
And
it's plugged in.
Whole thing.
Team, don't answer it.
two cuties.
Don't do it, Team.
Okay, so I want you to talk over this with your shoulder partner.
Yeah. I read this out.
Is that a question for you? Okay, you can always say improper or mixed, but either way is fine. Just don't say 2.6.
So 7 is 2/3.
2/3 of the whole thing.
Oh, yeah.
So
There we go. QT was.
So you divide by 2, 3.5.
So 10.5 is the whole thing.
Yeah. HQ 3.5.
Yes.
That's easy, my
Because
man.
we need 2, 3.5.
No,
You're bad. You're so bad.
Facts, not actually look at them.
Yes, you do. QT is literally 10.5. What do you want back?
Oh,
HQ is just half of HT.
not the actual.
You don't want to get good.
We got 7.
All right.
But I just.
Did we get fractions for both here? Yeah, I would imagine so. Okay, doesn't matter which one you fill out first. I think it's easier to do HQ and then QT. There's a couple ways you can go about this. So HT, which is my 2/3 chunk, 2/3 of the whole thing is 7. Then how much is that HQ, the 1/3 chunk?
3.5.
Good, I'm gonna leave it as a fraction, 7 halves. 7 meters. Yeah, 3.5 centimeters. So then how much is the whole thing, QT?
10.5.
So that'd be 11 over 2.
No.
If I can think,
So 10.5 or 21/2 centimeters.
I think no.
So let's think through possible ways we can do this. I know that HT is my 2/3 chunk and HQ is my 1/3 chunk. So again, if you remember that relationship between them, HQ being the 1/3 chunk is only half of my HT. So that's why I said half. Now, at this point, you could go ahead and add those together to get the 21/2. But let's think a bit back to our equations. If you don't remember those relationships, just go back to your equations. I know from my theorem that the measured HT is equal to 2/3 of the whole thing QT. I also know that the measured HQ is equal to 1/3 of the whole thing QT. These are the equations that we got from our original theory. So just go back to your original equations, and then just plug in what you do know. I know that HT is 7. So I can solve for QT. Multiply by 3/2 on both sides. And I get 21/2 equals QT. Here, I got that one first. That's fine. Well, now that I know what QT is, I can go and substitute that in. 21/2. We get 7/2. Again, probably faster to just divide it in half there. But if you forget, you can always go back to your original equations, just plug in what you know, and then simplify from there. Okay, questions with that? Yes?
What's the answer to the second goal?
Well, we're going to go back to that. Do you have questions on that?
Oh, get right.
Okay, so again, our centroid, just like with our perpendicular bisectors, we get circumcenter, which is equidistant from vertices. Angle bisectors, we get incenter, equidistant from sides. We now need to add to our memory. Our medians meet at the centroid, and that breaks it up into our 2/3, 1/3. So that is, I forgot when you go back. So that's our type of line. That's the point of concurrency, and here's that special characteristic. Okay. Now, our centroid is always inside the triangle. Last time we learned about circumcenter and incenter. which other one was always inside? In-center. So it's similar to our in-center in that it's always in-center. Okay, now this next bit of information, we don't do a whole lot with it. It's more like just a fun fact, but it's good to know. The centroid is also called the center of gravity of a triangle.
Oh.
Center of gravity of a triangle. Any thoughts as to what that means? Keegan?
It's like the point where we perfectly balanced on like a single topic.
Yeah.
Roll like this.
Yeah, so this is the point at which the triangle would balance. The point at which the triangle will balance.
Or do you get that in the center of gravity?
I wouldn't think so. It's more like a interesting other side of it. We don't really do anything
Why
with
do we
it.
implement physics to geometry?
Because it overlaps. Okay, so the idea here is that if we were to draw any triangle, no matter what kind, and find our centroid, so draw any triangle, draw your medians, find your centroid, at that point, you should be able to balance it out there. So, those tortilla chips that are in triangles, assuming that they would flatten them out, you could find that centroid. Guys, this is for you. You could find your medians, find your centroid, and then to impress that girl next to you, balance it out. She'll definitely be impressed. Alright. That's how my husband got me. No, I'm kidding. No, I saw him reading a math book across the room. That's how he got me. Alright. Questions with our median centroid.
Wait, what about the math one?
Just one of the many memories. I saw him in 7th grade across the room reading geometry book during our reading class. Caught my eye. Okay.
Read math during
During the reading class. Yeah. Well, it was free reading time. So
Were you high
I
school
choose
sweetheart?
read geometry. What else?
Were you a high school sweetheart?
I was reading Hank the Cow Dog. Take a fourth grade book. Anyway, that's enough about me. Altitudes. So altitude, vertex to side opposite so that it's perpendicular. Okay. If we draw all of our altitudes and meet at the point called the orthocenter. So our concurrency of altitudes theorem, unfortunately, is not very exciting.
Let's go.
It's just say it's the point is called the orthocenter.
The lines that contain the altitudes of the triangle, the lines that contain the altitudes of the triangle, altitudes of the triangle, the lines that contain the altitudes of a triangle meet at a point. And what do we call that point again? The orthocenter. It's orthocenter. And that is the end of the theorem.
Oh, wow, that's okay.
You made me leave so much.
Few words, we're not going to use this.
Sorry.
I was like, it's gonna be.
The lines that contain the altitudes of a triangle meet at a point. So all of our other ones had nice characteristics about this points of concurrency.
Not this one.
Our altitudes, they just meet the orthocenter. The orthocenter doesn't have any special characteristics.
My altitude's better than for geography.
Now, there are uses for altitudes, but our orthocenter just doesn't have a special property in relationship to our triangle like the other ones do. Alright, so sad, no property.
1997.
But our orthocenter, so again, we need to know that our orthocenter comes from our altitudes meeting up. And there is no special property. But our orthocenter can either be inside my triangle, on it, or outside. What other point of concurrency was either in, out, or on?
Circumcenter.
Circumcenter. Good. So again, last time we learned our circumcenter can be either in, out, or on. Same for our orthocenter, and it's in the same type of categories. If it's an acute triangle, it's in. If it's an obtuse, it's out, and if it's a right triangle, it's on. So conveniently drawn for you. I think altitudes are kind of the hardest ones to draw for our triangles. So down here are the 3 different scenarios. We have our acute triangle, right triangle, and obtuse triangle. You can see for our acute triangle, we draw all the altitudes. There's that orthocenter, always in. For our obtuse triangle, we have to extend out our altitudes. Like here's one of my altitudes, and here's another one of my altitudes. So we have to extend that out. And we'll notice the point is always outside of our triangle. That's for an obtuse triangle. And this is why the theorem says the lines that contain the altitudes, because sometimes we have to extend those out for them to meet up. Now for a right triangle, what do we know about a right triangle? What makes a triangle a right triangle? It has a right angle. Remember, an altitude simply connects vertex to side opposite so that it's perpendicular, so that it makes a right. So if I go from vertex to side opposite, it is already perpendicular, the side itself, because it's on the right angle. So my side, my leg, was actually one of my altitudes. Likewise over here, vertex to side opposite, here's my side opposite. If I want it to connect from here to this side in such a way that's perpendicular, it is that side once again. So for a right triangle, my altitudes meet at one point, the orthocenter for the right triangle. That always ends up being right here on that corner where the right angle is. So it is always on our right triangle, and it's always going to be right there where the right angle is. This is nice for when we do coordinate geometry. We've got a super short shortcut. Okay, questions about our orthocenter?
No.
So it's time to do some coordinate geometry with this.
Oh boy.
Woohoo!
Now, coordinate geometry, we said that we will have it with perpendicular bisectors, not with angle bisectors. You don't know how to bisect an angle on a graph. But we will also have it with medians and with altitudes. So just a refresher, we're doing coordinate geometry. Our ultimate goal is to write the equation of our line, whether it's median, altitude, or perpendicular bisector. In order to write the equation of a line, we need point and we need slope. So what pieces you have to find depends on which lines you're working with, which is another reason why it's important you know your vocab, because we need to know that our medians go vertex to midpoint. So if I'm trying to write the equation for my median, I need a point, you can use either one, and I need a slope. How do I find slope if I have 2 points?
Use sloping.
Sloping, yeah, slope formula. So I would use slope formula to get my slope, and I can use either point, and you can write your equation of the line. If we had our perpendicular bisectors, which we did this for home, perpendicular bisectors have to be perpendicular and bisect. So we need a point and a slope. Point, or bisects, which is our midpoint. Slope, find your slope and then do opposite reciprocal to get a perpendicular. If we're talking about altitudes, then you need to know what an altitude does. Altitude goes through vertex, perpendicular to the opposite side. So our point, the vertex. Our slope, gotta find our slope and then do opposite reciprocal to perpendicular. So we have coordinate geometry with each of these 3 categories, but you need to make sure you know what these different lines are to know which points you use, which slopes you use, whether it's perpendicular. So let's go take a look at these ones. We're going to focus mainly on our orthocenter here. So again, orthocenter, that comes from our altitudes. So our altitudes go through the vertex. This would be our point. And they have to be perpendicular to opposite side. So that's going to give us our slope. We have to first find our slope and then do opposite reciprocal. These are perpendiculars. Okay. again, we've got that super short shortcut. If it is a right triangle,
So,
it's just this guy right here. So first, check to see if it's a right triangle, and then you can use the shortcut.
It is.
Alright, so let's go take a look at number 8. I'm going to just do a rough sketch. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So here's A. B is 2, 4. Oh, that looks promising. C is 6, 0. Oh, what type of triangle do I have here?
Right
A
triangle.
right triangle. Remember too, I can just look at my points, and if I have X repeated, then that's going to be my vertical side. And if I have Y repeated, that is my horizontal side.
And the point.
If I have a vertical and horizontal, that makes that perpendicular. Okay, so my orthocenter is just simply that corner where the right angle is. And what point is that? 2, 0. Which is simply the one that has both.
Shared coordinates.
Sure. Okay, so here's my orthocenter. Nice and easy one's a right triangle. But I have to make you do some math today. Number 9. Do a quick sketch. We can also double check. Hey, I've got repeated Y's. Woohoo! Did I have repeated X's though?
No.
So it's not a right triangle. We have to actually do something here. I'm just again going to do a rough sketch. It just helps me out visually. 1, 2, 3, 4, 5, 6. Okay. So I have A, 1, 1. B is 3, 4. And C, 6, 4. You know, even though it's not a right triangle, at least I've got a horizontal side. That's helpful. Although it doesn't look horizontal the way that I drew it there. Okay. So orthocenter comes from our altitudes, which have to be perpendicular and go through the vertex. It's up to you which 2 altitudes you decide to do. I'm going to go and start off with an altitude to this side because it's horizontal. So if it's horizontal, it's perpendicular to it. Vertical! Alright. So it has to go through our vertex, the side opposite. What is going to be my line? Here's the point that it went through. So x equals what?
X equals 3.
Yeah, x equals 3. It has to go through my B point. And that's 3, 4. So it has to be that xy. Sweet, we have one of our lines. Awesome, that was nice and easy. Now we have to find the equation for another one of our lines. Doesn't matter which side you use. I'm just going to go and use side BC. Alright, I always have a hard time drawing my altitudes, but we're just drawing it just to have an idea of what we're doing here. So, vertex opposite. Here's my altitude, so it's perpendicular. Okay. So, it goes through point A. So, I have my point. But I need my slope. It has to be perpendicular to slope BC. Or sorry, perpendicular line BC. So what is my slope for BC? You can just do our slope formula, right? So you do BC. 1 minus 4. Oh, you guys do that so quick. Hold on. 1 minus 4, so we get negative 3. 6 minus 3. 3. 9. Good. So our slope of the original line was -1. So what's my perpendicular slope then? 1. Okay, so now I can write my equation of the line. Y minus, so I'm using my point, I'm using my slope. So y minus 1 equals 1 times x. Oh, come on, that's
X minus 1.
So I've got my equation of one of my lines. I've got my equation of my other line. Just do substitution to solve. If we didn't have a nice vertical line here, and it was another y equation, then we'd probably use substitution. But we have to use substitution here. Just take this and substitute. What do we get for y?
3.
Alright, so they meet up at the point x equals 3, y equals 3. So my orthocenter is the point 3. Again, they could have asked us to instead find our centroid, which comes from our medians. And our medians take vertex and midpoint. So we'd have to first find midpoint for 2 of our sites. And then we can write our equation using one of those points and our slope from there. Okay, questions with this? Yes?
How could you find the coordinates of A and use lines?
So my altitude has to cross through the vertex and the side opposite. So I needed to know my slope of BC, so I could do perpendicular to get my slope that's going to be of the altitude, so perpendicular slope. But my altitude has to go through my vertex A. So I'm writing the equation for my altitude. So the point it goes through, guaranteed, is my vertex. And the slope it has to have is perpendicular to BC, so opposite reciprocal to BC. Anyways,
So we don't have to find the midpoint to find the orthocenter?
no, so altitudes give us our orthocenter, and altitudes have nothing to do with midpoint. It goes to the vertex and is perpendicular. Medians, though, medians have nothing to do with perpendicular. They go vertex and midpoint. So you would have to find your midpoint and then do slope formula to get your slope. Yes?
So you could use like BC, or no, you could use A, B, and then C. Like for
Yeah, so instead of using side BC, I could have used side AB. Find your slope to opposite reciprocal, and it has to go through point C. Other questions? Of course, we hope and pray that I give you a right triangle one, because those are easy. But to be prepared, basically. Okay, we're not going to do constructions today. We'll keep doing constructions during Stinger. But I want to look at kind of a recap of all this. Again, you need to know your vocab, be able to identify the terms, but you need to know which goes with what. So this is a beautiful picture from our textbook. Let's go ahead and perpendicular bisectors, they drew their perpendicular, but I don't like that they didn't put in that they're bisected, so let's just go and add that information. I know they're telling us they're the perpendicular bisectors, but just so that you have that reminder that we need to know it's actually bisected. Okay, so perpendicular bisectors meet at the circumcenter. And its special property is the circumcenter is equidistant from vertices. Angle bisectors meet at the incenter, and its special property is that it's equidistant from the sides. And remember, it's not the continuation of your angle bisector, but rather, when we're talking about distance from a point to the side, that perpendicular distance. So I'm going to put this in parentheses perpendicular. Alright, our medians meet at the centroid, and that is 2/3 the distance away from the vertex, leaving 1/3 of the distance away from the side. So that's my 2/3 chunk. That's my 1/3 chunk. And orthocenter is where all of your altitudes meet up, and this has no special property. So it's kind of a summary of what we've done the last 2 days, the meat of our unit. And then just additionally, we have circumcenter can be either in our triangle, on it, or outside of it. And center is always in. Centroid is always in. And orthocenter can be in, out. And even more so, we could say it's in for acute, on for right, out for obtuse. Ah! I wanted to clone it.
Talking face.
Which is the same.
Wrong color.
Don't you worry, I got it.
Oh.
And we could even say even more, super short shortcut. That for circumcenter, the midpoint of the hypotenuse. Whereas for our orthocenter,
First picture is right angle.
vertex, the right. Okay. So again, it's really important to use flashcards, use Quizlet, use whatever you need to help you know this information, but also what pieces go together. Alright, your homework for today, I think it's just one worksheet, right?
Yes, go.
Let's do 4. In your way.
Really, 1.5 hours.
But really make sure you're studying these terms. If I were to give you a pop quiz next class on what goes with what, you should be able to ace it.
Yeah, I don't understand.
Oh.
I understand how complicated I don't know.
It's true. I warned you that it's technically not a pop quiz.
That's bad.
Oh, this is easy. This is easy.
Wow.
You can get one.
Move up
More experiment here.
I'm gonna go.
Okay, one more.
Watch, it's like,
Get home.
I'll
be down.
Is there one that did not get worksheet 4?
And then go.
Need one more.